Maggie Fowler, and I will be talking about Lab 4. The premise of this lab was predicting and observing the behavior of circuits consisting of resistors and capacitors in parallel and in series. We used ammeters and voltmeters to measure conventional current and potential difference respectively, using an online interactive circuit model. The physics principles we used were the loop rule, which is energy conservation, and the node rule, which is current conservation. The first thing we did was make a prediction about a simple circuit. By using the loop rule and the node rule, we got that I1 should equal I2, which is 0.02 amps, and this prediction was correct. Next, we made some observations about the simple circuit. So by reversing the connection to one of the ammeters, you would do this by reversing the orientation of the batteries, and the ammeters will continue to read 0.02 amps because they only give the magnitude of the current and not the direction. Then we replaced one of the ammeters with a voltmeter, which you see in this picture, and in this case, the current goes to 0 because voltmeters have infinite resistance, so the current is not going to flow through the voltmeter. And then the -3 that you see here, all that means is that the red is at a lower potential than the black. Next, we use the voltmeter to solve for the change in electric potential at different points along the circuit. So from A to B, with the red node above the black one, we got 3 volts. From C to D, we got -0.959 volts with the red below the black. And then from E to F, it was also with the red below the black, and we got -2.041 volts. And then along all the wires and the ammeter, we got 0 for our change in electric potential. And the whole time the current read 0.02 amps. Next, we made a little graph of the electric potential relative to the negative end of the battery. You'll notice from D to E and from F to H, there's no change in electric potential. And then from C to D, it goes down 0.9059, and from E to F, it goes down 0.2041. Next, we used our delta V's we calculated earlier to solve for the resistance of the 47 ohm, 100 ohm, and of those resistors. So for the 47 ohm resistor, we got 47.95 ohms. For the 100 ohm resistor, we got 102.05 ohms. And then, of course, for the wire and the ammeter, we got 0 ohms. Next, we made some observations about multimeters in parallel. So earlier, when we were calculating our change in electric potential, the ammeter reading never changed, and that's because we were adding the voltmeter in parallel. Since voltmeters have infinite resistance, the current's always going to go through the path without the voltmeter, so no current's going to ever go through the voltmeter. And then we connected the voltmeter across the 100 ohm resistor. Again, the ammeter reading didn't change because the voltmeter was in parallel. And then we replaced the voltmeter with an ammeter, and now the current does change. It switches to 0.06, and that's because ammeters have 0 resistance, so the path through the ammeter is the path of least resistance, and that's where the current's going to go. So the current's only going to ever go through the 47 ohm resistor, which is why the current changes. Next, we made some observations about capacitors. What we did is we got a series with one battery, a light bulb, and a capacitor, and then we observed how the light changed. So when we first started it, the light got bright almost immediately, and then it went out gradually as the electrons stopped moving and the capacitor finished charging. And this is because the current went to 0 as the capacitor charged. So when the capacitor was fully charged, the current was 0. Then we disconnected the battery while the capacitor was fully charged and just had the capacitor connected directly to the 10 ohm light bulb. And what happened here was the light got bright almost immediately again, and then it gradually went out as the capacitor lost charge and the electron slowed down. And then with the current had started up again almost immediately, but then it went back to 0 as the charges left the capacitor and the circuit reached equilibrium. The observations we made here was that it took 19.71 seconds for the capacitor to charge using the 10 ohm light bulb. It took 19.65 seconds for the capacitor to discharge using the 10 ohm light bulb. It took 39.27 seconds for the capacitor to charge using the 20 ohm light bulb, and 39.21 seconds for the capacitor to discharge using the 20 ohm light bulb. Next, we made some calculations for the RC. So what we did here is we got the capacitor to get all the way fully charged, and then we took time and voltage as the capacitor was discharging for 20 seconds, and we plotted the Ln, and we know here that the slope is supposed to equal -1 over RC. So the RC we got from our graph, it was 6.00024, which agrees with what the RC should have been, because that's just resistance times capacitance, so that should be 30 ohms times 0.2 farads, which is 6. In conclusion, if we'd done this lab in real life, an actual ammeter would not have 0 resistance, and so the current would decrease in the circuit. And then if we had done this lab in real life using a battery to charge a capacitor, and there was no resistor in the circuit, our ideal model would predict the capacitor would reach full charge immediately, whereas in real life there would be some resistance due to the battery, capacitor, and even the wires, so it would take some time for the capacitor to charge.